So far we have only seen MM1 systems. So how do we extend that analysis to systems where there are multiple servers in a given queue, serving a given queue. So in a load dependent service center, previously we had right mu or SI was simply just 1 over mu, but now the service rate is now going to depend upon the number of customers in the queue. So when there is only one customer, the service rate is simply mu, right? We saw this when we did the MM1 system or MMM system. There are 2 customers, service rate is 2 mu, 3 mu and so on. So therefore the effective capacity of the system changes with the number of customers in the queue. That's the only change, which is not new to us, we know that. So the effective capacity of the system when there are n customers in the queue is defined as follows, right? So if S is the service time, so it is simply 1 over S, right? Remember that the capacity is 1 over SI, in this case just S, right? I could have, let us say this is, I will just use this to be precise. So in ith queue's capacity when there are n customers in its queue is simply n by Si. For n up to m minus 1, and where m is the number of servers. So where Si is the service time of the ith device, and m is the maximum number of servers at ith device, right. So basically your MM server. So this is another way of defining it, right, that the service rate of this queue varies with the number of customers waiting for service. Okay, so now a couple of definitions. C I J. So this is defined as the probability of finding j jobs at q, right. If it is MM3 there are 3 servers
in this system,
in the ith device. So every device is now, so what we are looking at, okay, I should probably just come back, right. So now I am defining a queue of networks where there are multiple servers available, right. Previously only one server was there, and then collectively this feeds into another queue which could also be a multi server device, right, and then this feeds into another queue and so on, which might be a single server device. So you might have a system like this. Okay. So there are m such servers, right. So this is a collection of MMM queues. And so on. So this is, so Pij of n is probably finding j jobs at Qi, given that there are n jobs in the system. Again this is for a closed queuing network. Okay. So with that definition then we will try to define some things. So Ri, which is the response time at server I when there are n jobs in the system, is given as follows. Does it make sense? So if there are j jobs at a given point in time, right, that is simply the probability of this jth job finding j minus 1 jobs when there are n minus 1 jobs in the system, right. So this is p j minus 1 n minus 1 is the probability of having j minus 1 jobs in the ith queue when there are n minus 1 jobs in the system. Then your jth tag job comes along, therefore the total service time is simply j divided by mu of j, right. Make sense? I don't think on a Friday afternoon some of you are saying yes, others are like what the heck. Yeah, this is the average response time at the ith device depending upon the number of customers in the device. When there is only one customer, or let us say when there is only 2 customers, the response time is given in this manner. So the number of customers in that particular queue can be anywhere from 1 to n. So I am just summing over all those probabilities of 1 to n. In the system, yes, out of which they could all be sitting in this queue or they could be sitting in some other queues too, right. So when there are j customers in the queue, the delay is given by p of I minus 1 or j minus 1 n minus 1 into j divided by, again j is the number of customers, right. So because each customer requires mu I of j service time, or mu j service time. Okay, so that is not that hard if you spend another couple of days on it, okay, if you want to. And then so now this magical probability j of n. So how do we compute this? Because once I compute this, then everything else falls into place. Okay, so this is actually we are not deriving this, unfortunately. This is defined as x of n by so this is defined recursively. So this is, well, I will have to go back and dig up some of the other queuing network books to actually, what is the connection to x by mu? X is the number of, x is the throughput of the system, right. So throughput into, so this is the average number of customers completing their service at this queue. Okay, I do not have the intuitive explanation for that, I have to do some homework on that.
How are we dividing it? N systems in n customers in systems.
No, all it says is that if there is only one customer, right? Let us say the queue is there are 8 100 Mbps links. Only one packet is in the queue. The capacity of the server is 100 Mbps. When there are 2 packets simultaneously being served, the capacity is 400 or 200 Mbps and so on. That is what that means. So when all 4 servers are active, then the capacity of the system is 400 Mbps.
It can be possible also that
No, this simply says that at the ith job or ith queue rather, if there are n jobs, then the capacity of that server is n by si or m by si. If n is greater than or equal to m, then it becomes m by si. See, if I have 100 Mbps links and there are 4 such links, right, there is one packet in the queue, then the capacity of that system is how much? 100 Mbps, right. At that instant that is all it is serving, 100 Mbps. When there are 2 packets simultaneously being served, it goes to 200 Mbps. When there are 5 packets in the queue, it is still 400 Mbps because the others are getting queued. That is what this is trying to tell you. The effective capacity of the server is dependent upon the number of customers in the queue, and so on. So even if there are 8, it is only going to be 400 Mbps, and then Qi of n. So what will be Qi of n? Should I have write down, or can you just tell me what that is? What is the probability of I customers in this queue when, or so what is the, when there are n customers in the system, what is the average number of customers at Qi? Sigma j. So j goes from 1 to n, and then Pf, that is all, right. So Pij tells me that what the probability that the j customers out of the n residing in Qi, and that into j will give me the overall Qi. So now we have expressions for R and for Q based on this definition of P. So now again we will have this recursive step where you enumerate from, right, for the different values of j as you go along. I think we have forgotten MVA after convolution. Okay, these are the expressions that are going to be changed with respect to the old MVA algorithm that we saw, that exact MVA algorithm. Okay, where we also computed, right, we computed Q, we computed then R based on the Q. Remember what we did? We said R equals S into 1 plus Qi, right, and then from the R we found Ri, we found out the R, from that we found the X, from that we found the Qis, and then we did went, right, repeated. So in this MVA version the same computation is being done, only the difference is that your computation of R is being done differently and computation of Q is being done differently, that is all. Otherwise it is the same model that we saw with the exact MVA approach. Okay, so the algorithm itself is kind of, you know, similarly repetitive. So this is your MVA with the so called load dependent service center. I think once I write the algorithm, will so far so this is the exact MVA. So we start off by saying that Qi equals 0, right, and then we built up from Qi1, Qi2, Qi3 and so on. So the so this is for the fixed capacity and delay center. So I have now a set of queues, some are fixed capacity, some are delay centers, and some are this load dependent service centers, MMM systems. So we will have to run MVA for this entire system and find out the throughput and other things. Okay, so now we have to set this to 1. What is the probability of there being 0 customers when there are 0 customers in the system? Probability of 0 customers at Qi, right, when there are 0 customers in the system is simply 1, that is the initialization. By the way, the book is, the book gives this as 0 and that is incorrect. So you start with 0, everything will be 0 if you look at the rest of the computations. So that is an error, it is there in the errata but not in the chapter itself. So make sure that you note this down, do not make this mistake when you come to the exam and start with 0, you will never, you will get 0 for everything else. So this is your initialization, okay, then your iteration, okay. So for then it is so now for given a value, input value n, we write, remember we compute Q, the input, the values for n equals 1, then based on that values for n equals 2 and so on, just like we did in the exact MBA. So this is now for every q so what is Ri? If it is a fixed capacity center, it was Si into 1 plus Qi, remember when there are n minus 1 customers, what is the Q length, then plus myself into the service time, that is how we calculated this. So if it is for any I that is a fixed capacity right center, this is your Ri. So this is, look at this as a switch statement or a case statement, right, and Ri equals Si if it is a delay center. So depending on what I is representing, you would change your formula. So I will put R oh sorry, not R. So n is your current value, right, of the index, the outer loop index. Remember this is what we did, Ri equals when there are n customers, right, there I had this extra j minus 1 and then if n minus 1, that if n minus 1 is what I have removed because that is implicit, I just need this one array Pi to do that, I do not need the 2-dimensional array, right. So it is simply if there are j minus 1 customers in the system, then what is the into j. So that is why if when I start with say n equals 1, I will need Pi of 0 and Pi of 0 better be 1, if that is 0 then I will not have, everything else will end up being 0. So that is why that book error is an error, okay. So this is it, so I get my, this is my end of for loop, right. So I have computed the Ri's. Then I compute my x, okay. So this is what we did the last time too, no change. Now the next step is when we compute, there we recomputed the Qi's, here we will recompute the Pi's based on the previous values, okay. Alright, so then again so remember how we computed Qi is equal to x into xi into Ri, that is basically x into Vi into Ri, right. So we recently calculated Ri, x is also recently calculated, so we update the values of Qi, this is basically Qi of 1, right, this is if it is a fixed capacity server or also delay center, it does not matter. So here we have a little bit of a loop, so for j equals 1 to n, oh sorry, there is one mistake in the book and which also has to be corrected, this is not, this is lowercase because for n customers, right. So this is again book will say book is in error, if you use that formula that is it, you will be getting the wrong values of x because n is the original input, right, because n is 20, that should not be used here, the current running value of the n variable is what should be used. Any other place where this n is appearing? This loop is for I equals 1 to m, so for a given value of n I am computing all the Ri's, I am computing the R, then the x, and then I am recomputing the Qi's to go to the next iteration of n, or rather this is done the reverse way. Small n will go from 1 to say n, big n is 20, it will go from, like we did MVA, right, we compute n equals 1, what are the Q lengths, n equals 2, what are the Q lengths and so on. So this is for a given value of n within the, So for this we will again use that expression that we saw, right. This is the definition of Pi of j, this is your x of n, right, that we just computed divided by mu I of j into Pi of j minus 1. And then Pi of 0 is simply 1 minus right. So this is for load dependent. Okay, there is no other place where uppercase n appears. Okay, good. So that's the, so this is as it is before. This is the only change based on the PIs that we saw before. Okay, and then that this loop is closed. Yeah. Okay, this closes the. Yeah, this is for. Is it for n equals 1 to n loop. So at the end of the n iterations you finally have the value that you want. So what you have is x of 20 or r of 20 and so on. Okay. So then we can do the right. So final so final calculations you will do xi equals x into vi, right. This is for all I, and ui is simply xs, right. So xi si, this is if it is a fixed capacity center or delay center for whatever values of I that match it, and in the case of this one it is simply so Pi of 0 is the probability that there are no customers in Qi at the end of all the calculations, and 1 minus that is simply going to be your utilization of the particular queue.
Go back to the beginning of the iteration.
Beginning of the iteration we are computing the RIs depending on whether it is a service and fixed capacity or delay center or load dependent service center, right. That is this loop here. So once I compute the RIs, I compute my R and X like I have done before. Then once I compute my X, I go back and recompute the QIs for all the devices. That is what this loop is all about. Why does QI come for yeah, that does not matter, that is just for the sake of let us see where will we use that. It's only to when you compute the final yeah, QI will be simply the number of customers that are in the thinking state, right, number of terminals that are in the thinking state, that is what your QI is. It's still the QI will be simply rho I, right, the QI in that case will be equal to UI, which is the of course we do not really have Vi for that the delay center, right. Yeah. So this is all the other than delay centers is where that RAVI is coming into picture. Okay, I think we have enough time for a numerical example and we will call it quits. Okay. So this is a sort of funny looking example. The reason for this will be evident when you look at the next section, right. So this is actually to serve the next section. So we have this is your symbol for a and we will call this device as FEC for now. Okay, so jobs come from here to this disk and then from the disk it comes back here, okay, or it goes here. This is your loop. Only two queues, one is a fixed capacity queue, this is your fixed capacity center, this is your variable capacity center, and the definition for this is, so here Vi is equal to 6, Si equals 0.26. We saw the same fellow before, this disk B, 0.6 and 0.26 and 6, right. What is happening here is that disk A and that CPU have been sort of collapsed into this so called this variable capacity center. How we do that we will see later, but this is now the definition for this queue, right, is as follows. So this is J and this is mu A of J. My box looks kind of weird. So when there is one customer, the service rate is 0.32, when it is 2 it is 0.39, when it is 3 it is 0.42. This is a little bit different from what we saw so far, right, where it is always a multiple of the number of customers. Here it is not a multiple, but so this is true for any value of mu. You can define whatever combinations, right, when the expecting that as your number of customers increases, your capacity also increases, that is all, that is the only real relationship. In an MM1 system, M system, as M it is proportional to M, right. And also note that there is nothing defined for M greater than 4, which is also fine, right. So in this case you cannot have more than 4 customers for whatever reason, at most 3 customers can be in this case, okay. So this is our input so far, okay. So only 2 queues to worry about. This is your variable capacity server depending upon the number of customers in that queue. So the initialization parameters, so remember QB, right, QB of 0 equals 0. When there are no customers, there are no, in the system itself there are no customers here, and P of 0 comma 0 equals 1. So for a load dependent system we use the probabilities Pjn, right. This is 0 customers in this queue, when there are 0 customers in the system that is always equal to 1. So this is our starting point. So now we go to iteration 1. So n will take the value 1. So what if there is only one customer in the system that is circulating? So RB of 1 is simply S, right, SB into 1 plus QB of 0. In the algorithm we did not have this parenthesis of 0 and so on, but this is what it is. So this is 0.26, right, into 1 plus 0, therefore this is 0.26 again, and R FEC of 1, remember this is summation going from 1 to n in this case happens to be 1. So this is simply P FEC of, or P0, right, this FEC also will drop because this is the only device which has this probability. So it is simply P00 into J, so J is 1 divided by 0.32. So this is, so that is how your first iteration for this R is computed. So then you recompute R oh yeah, and another input is that your, I said V, right, this is VB, here your V FEC equals 1, only one visit to that. Alright, so QB of 1, right, the updated version for the queue length is now based on the new X that we calculated, so X into RB into VB, so that is now 0.33. So from QB of 0 it is now updated to 0.33, Likewise P of 0 0 was 1, now P of 1 1 is what we are computing based on P 0 0. So that is now updated to 0.67, and if you look at the expression we compute everything from 1 to n, and PB of 0 or P of that 0, right, the number of customers being 0 in the ith queue, it is simply 1 minus the probability of all the other sum of all the other probabilities. So this is the probability of one customer in the that variable capacity center when there is only one customer in the system is 0.67. The probability of no customer in this queue is when there is only one customer in the entire system is 0.33. That is what this is trying to compute, right. This is your first step of the iteration. So then we go to the second step. So now my n gets the value 2, and then we repeat this whole thing again. So QB equals SB into, so this is now QB with 2 customers, right, this is with QB with 1 customer. So that is 0.26 into 1 plus 0.33. Oh sorry, yeah, so this is RB, but this is QB, yes, no. Okay, there, okay, Q, R and S are in proper places, okay. So now this is 0.35. So that is our, this is a standard update we did the last time, right. So only now the probabilities are going to be different. So now the probability of okay, so this is now R, right, FAC with 2 customers equal to the probability of one customer or no customers in this queue with overall one customer into J by, so this is J by mu of J, so then J takes the value . So J is 1, this is J minus 1, this is n minus 1, this is J minus 1, this is n minus 1, right. So in this case J is 2, rather sorry, J goes from 1, J is either 1 or 2 and n equals to 8. So this is 0.33, this is 0.32, this was 0.67 into 2 divided by, this was 0.39, right. So now your new R value gets to be 4.46 seconds. So it is kind of repetitive after a while, but that is the basic idea. But this helps you find what you are looking for, right, if you have such kind of system. So now R of 2 is now computed like before, RIVI, and that is now updated to 6.54, then X of 2 is now 2 divided by R of 2, and that is 0.31 and so on. Okay, is that followed? Then we do all the updates. So QB of T or 2 is X into your VB into RB of 2 or X of 2, and that is now updated to 0.64. So the Q length increases to 0.64. So now we have to compute the P 2 2 1 2 and then 0 of 2. So P 2 of 2 is given by X of 2 by mu of 2 to P of 1. So this is 0.52. Then P of 1 comma 2, right, again. So P of j comma n is given by X of n, which is that, by mu of 1. So remember that. Then it is j minus 1 and minus 1. So this is p 0 comma 1. And that is nothing but 0.32. So now what you find is the probability of both the customers being in this FEC when there are only 2 customers in the system is fairly high, or 0.52, and then one customer is 0.32, and therefore no customers is simply 1 minus p of 2 comma 2 minus p of 1 comma 2. So that should be 0.16 we hope. Yeah. Okay. Oh wow, time to wrap up. So this is the end of our second iteration. So third iteration I will let you figure it out. So now our FEC of 3 equals what, right? So again j goes from 1 to 3, so therefore it is j divided by mu of j and then p of j minus 1 and minus 1, right. So if when j is 1, so this is 0 comma 2 into 1 by mu of 1. When j goes to 2, then this is 2 by mu of 2. When j goes to 3, this is, did I get all that right? Yeah. This then finally computes to 5.86. Now QB we know that is simple, or sorry RB, keep making that. Right, this is and so on, right. So once you get the r's, you get your i's, you get the r, then your x, and then repeat this. We will have one more iteration, but that we do not have to worry about, but in the end you will be able to get the throughput of the system and so on. Okay. So that is the, so in the final result I will just write that down. Your x is finally going to be 0.36 and your final r is going to be 8.4. Okay. So we will stop here. Questions before we wrap up? So this is the way that you can now bring in the variable capacity servers also into their system. So programming assignment 3 requires you to implement a bunch of MMM servers and solve that with simulation, and then solve this by a simple program and then compare the two results.